So let's talk a little bit about collisions specifically. And there's two types of collisions. And what we're going to do is we're going to tie momentum and energy together. So we'll have elastic and inelastic. And it's really perfectly elastic. So we'll talk about each of these in turn. So let's start with inelastic collisions. So inelastic. And we really would say perfectly inelastic. Perfectly inelastic. What this means is that they're sticky collisions. You could say it that way as well, sticky collisions. So this is when you got two balls of clay and they collide, so they stick together, and then they go off at some velocity. So this would be an inelastic collision. The inelastic refers to a deformation of the objects. So deformation. So a car crash. Car crash is not perfectly inelastic, but it is inelastic because you'll have a car, and then you have another car, I'm drawing them kind of exaggerated. So if these two cars collided, they'd probably bounce off of each other, but they'd be damaged. The hood would get dented in and all this stuff would, so we'd have a deformation, however, they wouldn't stick together. So that would just be an elastic. When they stick together, that's perfectly inelastic. And that's really what we're going to be analyzing, are these where they stick together. So perfectly inelastic. And the things to remember is that in a perfectly inelastic, momentum, of course, is conserved in an isolated system. Momentum is conserved. But total mechanical energy, so kinetic and gravitational, total mechanical energy is not. Okay? So momentum is conserved, energy is not. That's for inelastic. All right, so let's look at an example. So in the lab, we have a 200-gram air track glider and a 400-gram air track glider, and they're pushed towards each other from opposite ends. These air track gliders, that just means it's frictionless. The gliders have Velcro on the front and will stick together when they collide. The 200-gram is pushed with an initial speed. The collision causes it to reverse direction at 0.4 meters per second. What's the initial speed of the other glider? Okay, so let's just draw this thing. Let's sketch it out. So we'll have call it mass 1, and this mass is going to be 200 grams, so 0.2 kilograms. And then it has a velocity of 3 meters per second. So the initial velocity is 3 meters per second. All right, so this one's going to be going this way. And then we have the second one coming this way. We'll call it mass 2. The velocity here is, we don't know. That's what we want to know. But we know the mass is 400 grams, so 0.4 kilograms. And then they stick together. So we'll draw a little line to do our after. So they stick together. So we have mass 1, mass 2, and it causes, when you read it, it says that it causes this one to change direction and go this way. So the velocity is going to be 0.4 this way. All right, so I think we're good. What's the initial speed, blah, blah, blah. Oh, the total mass over here is going to be mass 1 plus mass 2. All right, so let's see. Well, we know that the momentum of the system is conserved. So the initial momentum equals the final momentum. So we're going to have, let's put some numbers on here, mass 1, mass 2. So mass 1 times the velocity of 1 initially plus mass 2 and the velocity of 2 initial is equal to mass 1 plus mass 2 times the final velocity. And that's the final velocity of the combined. And we're targeting this variable here. So let's see what we can do, see if we can solve for this before we put in some numbers. So we'll subtract this over to the other side, and then, m2 v2 naught equals m1 plus m2 vf minus m1 v1 naught, and then we'll divide the whole thing by this m2. Yeah. All right, I'm going to do some calculations real quick. I'll pause it for a sec. Okay, so you plug in all your numbers up here. You plug them into this thing. Keep in mind this velocity. See how it's going left? So that's a negative 0.4. So when you plug it in, make sure you put the sign correct. So what you end up with is the initial velocity of this second block is negative 2.1 meters per second. So negative 2.1 meters per second. 2.1 going this way. All right, well, let's go ahead and we'll do another example. You know, before we do that, let's go ahead and, since this is an perfectly elastic collision, let's go ahead and check the kinetic energy just to verify that it's not conserved. So let me move this down a little bit and get some room. So we're going to check the total energy of the system. So it's going to be 1/2, this is kinetic energy, m1 v1 naught squared plus 1/2 m2 v2 naught squared. And we're saying, is that equal to 1/2 of m1 plus m2 vf squared. So we have all these numbers now, so we can just plug them in. I'm not going to write them all down, I'm just going to put it in a calculator. All right, so plugging it in and calculating, what we see is that the initial kinetic energy was 1.782 joules, and then we got 0.048 joules afterwards. So we can see that these are clearly not equal, and in fact it decreases, and this is what always happens. We lose energy, and so the question is why? Why do we lose energy in an elastic collision? And it just goes back to the definition of an elastic collision, that there's going to be some deformation, and because you have an object that deforms, that takes energy. So we have to rearrange, you know, all of the molecules that are forming it. We have to rearrange them and move them over here, you know, to get some kind of deformation in the object. Well, that takes energy. And so it's this kinetic energy that gets transformed into some deformation. All right, let's look at another example. Okay, so I've gone ahead and drawn this out before starting to talk about it. But this is the classic, it's called a ballistic pendulum. And so what we have is we have a bullet that's flying towards a block of wood that's just hanging by a thread. And when the bullet gets embedded, then the block will swing up a certain angle. And so if we know some of the measurements, we can actually determine the velocity of the bullet. And you know, back in the day, this is how they would determine what is the velocity coming out of a gun. And so to do this, we're going to have to do a couple different things. And so I'll talk you through it just to give you an idea about the analysis that we'll take. So since this has some velocity, we know that we have some, but we have both kinetic energy and momentum. So we have both kinetic energy and momentum of the bullet over here. We can figure that out if we knew the velocity, right? But then it gets embedded. So once it strikes, we now have an inelastic collision. So we know momentum is good. Momentum is good However, the energy is not. So our mechanical energy is not conserved for the collision. Okay, so we can call that like part one, just when the bullet collides. So we have this collision. And then we have the second part. The second part is when the block actually gets swung up. And since the bullet is already embedded, we don't have a collision. So we just have this block that starts with some kinetic energy, and then the kinetic energy slowly dissipates. And so all of in that system, the total energy, the mechanical energy, is conserved. However, we can clearly see that the velocity, the mass doesn't change, but velocity does. So momentum is not conserved. And so what we can do is we have to do a combination of these two analysis. We'll use momentum over here, and then we'll have to use energy over here, put it all together, and we can figure out what that velocity of the bullet is. And so we begin with the first part, and we're just going to try to get an equation for the velocity of the bullet, and then we'll come over to kinetic energy. So I'll go back to green for the first part, the momentum. So for the first part, we'll call it the collision. So the total momentum, the momentum of the bullet, plus the momentum, I'm going to put W for wood, the momentum of the wood initial is equal to the momentum of the bullet wood over here, right when it gets embedded, not over here, just right here. Okay, so we have the mass of the bullet times its velocity of the bullet. And I don't have to add on the block, it's sitting still, so there's no momentum. And then after they get embedded, then we have the mass of the bullet plus the mass of the wood times the velocity. And we'll say the velocity of the bullet wood. Yeah. Okay. So to get this, we would just divide. So the velocity of the bullet is going to be the mass of the bullet plus mass of the wood times the velocity of the block wood over the mass of the bullet. And that's as far as we can get. We don't know this quantity here. So once it gets embedded, we don't know how fast it's going to begin with. So now we need to go over into energy. So to begin with, this is going to start with all kinetic energy. Like after it collides at that instant, it almost immediately is going to have some velocity, and then that's quickly going to transfer all into potential energy. So let me switch to yellow for this part. So we have some kinetic energy to begin with. And again, I'm analyzing from here forward. So the kinetic energy is equal to the gravitational potential. So we get 1/2 of the mass of the bullet and wood times the velocity of the bullet wood squared is equal to the mass of the bullet wood times g times h. So this is just using our energy stuff. Yeah. The problem is that we don't know this. So let's see, what could we do? So what if we were able, over here we know the only thing that we don't know is going to be this, the mass of the velocity of the block wood to begin with. So let's solve for that, and then we can use that quantity, plug it back in here, and that will give us our velocity of our bullet. So first thing is just notice that we have the mass of the block wood on each side, so we can divide that off. So we get 1/2 of the velocity of the block wood squared is equal to gh, and then we'll multiply each side by 2, so we get the velocity of the block wood squared is equal to 2gh, and then to cancel the square we would take the square root. The problem here is that we don't know h. Okay, but can we figure it out? Sure, why not? So we go back here, we have to use some trig. So the idea is we basically want to come across to form our right triangle, and my height is going to be this distance right there. That's going to be the height at which it rose. So to get that would be this right here. Let's call that, well, to get it would be L cosine theta. That would be the distance from here to here. But I want the missing piece. So that would be the total length here is L. So my total height, H, would be equal to the length minus L cosine theta. That would be my height. So we could go ahead and we can just plug it in there for H, or we could just wait. I could calculate that. So anyway, I'm not going to plug it in because it's a lot to write. Well, you know what? At this point, we're kind of done, because we know all these quantities. L is, what was L? 1.5? Yeah, 150 centimeters. So L is 0.15 meters. So your height is going to be 0.15 minus 0.15 cosine of 40. Let me calculate that. You get a height of about 0.351 meters. So that would be our height. So now we can plug it in here and get our velocity. And doing that, you get a velocity of the block wood to begin with is going to be 2.62 meters per second. And now we'll take this quantity, and this is going to come back over there. And so we know the mass of the bullet and the mass of the wood. We know the velocity, and we know the mass of the bullet. So now we can plug everything in and finish the problem. So the velocity of the bullet would be the mass of the bullet, 0.01, plus the mass of the wood, 1.2, times the velocity, 2.62, divided by the mass of the bullet, 0.01. And when you do all of that, you should get, if I set it up all correctly, 320 meters per second. Seems reasonable for a bullet. All right. Seems complicated, but if you just go back and think about what we did, it's just that analysis of the momentum, then switching over to energy, and then coming back to momentum to finish. Similar to projectile motion, how we analyze that. Okay, so I think that's it for inelastic. The only thing with elastic is, well, let's just get a new page up real quick. Sorry, this video is running long, but it's this problem. No. Okay, so we have elastic collisions. So in an inelastic collision, momentum was conserved and energy was not. In an elastic collision, momentum is still conserved and mechanical energy is also conserved. So what's an elastic collision? That's a perfect bounce. So it comes down and springs back, yeah? Or you have two balls headed towards each other and they bounce off of each other. What kind of balls do these need to be? So tennis balls? No, not tennis balls. Because when tennis balls collide, they're gonna deform. You'll have this bouncy. So we're talking about like hard steel balls or something like that, or ball bearings, banging into each other. And then if they were solid, when they hit, they don't deform enough for there to be a loss of energy. Okay? Let's put some numbers on there. All right, just because it looks weird without numbers. Kind of looks like a face. Yeah. All right, you get the gist. Okay, anyway, that's all you need to know. So inelastic, energy changes. Elastic, energy does not change. And that should be it. You should be good to go.